What's going on, everybody? Mr. Diamond, and I have three separate example problems that we are going to work out related to momentum. I'm going to read through them really quick. If you'd like to pause the video and try to do these by yourself, I would recommend that. It's a good way to get practice and see if you're feeling good about these, or at least pause after the first or the second one and see if you can do the last one by yourself. Although I guess the last one's a little weird in this case. So example one, what is the magnitude and direction of the momentum of a 28.0 gram sparrow flying with a speed of 8.4 meters per second, ignoring air resistance? Number two, what force would be needed to cause a 4.5 kilogram toy car to increase its speed from 3 meters per second to 5 meters per second over 3.5 seconds? And then finally, a truck is driving at a speed of 8.8 meters per second when a chunk of rock weighing 20 kilogram falls into the back. If the truck originally weighed 3,500 kilograms, what is its new speed? And like I said, this one's a little bit weird. So let's go ahead and scoot the camera down, and we'll start with example number one. So example number one tells us that we have a bird, which I'm just gonna draw as a cube because I don't really feel like getting bullied for my bird drawings today. But this bird weighs 28 grams, which is the same as 0.028 kilograms, I believe. Yep, 28 grams. Remember, we want our units to be in kilograms for this. And it's flying with a speed of 8.4 meters per second. We're going to go ahead and call that to the right. And then it says ignore air resistance, and we want to know what is the momentum. Remember, the symbol for momentum is a letter P. Now this one is pretty straightforward. P, or momentum, is equal to m times v. So in this case, we're just going to multiply those two things together. 8.4 meters per second times 0.028 kilograms gives us 0.23, we'll go ahead and go 5.2. And that is kilograms per meters over seconds. Again, I know it's a weird unit, but that's what you use for momentum. And then it says it wants the magnitude, also the direction. Let me click and make sure on my actual one it says 8.4 meters per second to the east in the original problem. So our magnitude is this, and our direction would be due east. Easy enough. All right, example number two. What is the force needed to cause a 4.5 kilograms, so that's our mass, car to increase in speed? So our V1 is 3 meters per second. Our V2 is 5 meters per second over a time period of 3.5 seconds. Now, I'm only doing this in a line because I'm worried about running out of space, and I'm feeling really lazy today. I don't want to actually flip the page. But we should have enough space for this. So the important information here is that we know that our impulse is equal to our change in momentum, and because of that, we know our sum of our forces times time is equal to mass times change in velocity. Rearrange that to get force by itself. We get force is equal to mass times change in velocity over time. So in this case, our force is equal to, our mass is 4.5 kilograms, times our final minus our initial would be 5 minus 3 over 3.5 seconds gives us 2.57, and this unit would be newtons because it's a force, and force is in the unit of newtons. So notice that we know we're dealing with when we're asked about a force, that implies that an impulse is going to be necessary. And in this case, the only way we can solve it is if we know that impulse. Apologize for that yawn. Hopefully it didn't come across as too annoying. That impulse and momentum are connected to each other. Impulse is directly equal to the change in the momentum. In this case, the change in momentum would be our delta V. Okay. So number 3, I said, was going to be a little bit weird. So we've got a truck. I'm going to draw as just kind of like a flatbed. And it's riding along. And there is a rock that is going to eventually fall into said truck. A truck is driving along at an initial speed, so V1 is 8.8 meters per second. When a chunk of rock weighing 20 kilograms falls into the back. So this rock here is 20 kilograms. The truck by itself weighs 3,500 kilograms. And it's asking, what would its new speed be? Now, this is going to be a little bit weird, and you'll probably understand why it's a little bit weird when we get to section 2 of these notes, because there's an easier way to explain it, but I'm going to explain it in kind of the longer, convoluted way first. So you'll notice that there is no forces that is at least relevant to the thing that's happening here. Obviously, the rock falling is going to exert some amount of force into the truck, but if we're talking just about the moving to the side, there's no forces that are happening in there, which means if the sum of the forces is 0, that means that sum of the forces times time is 0, and that means that the change in momentum, the change in P, must be 0. And if that's the case, then that means that our momentum at the beginning must be equal to our momentum at the end. So what we're going to actually do here is we're going to set P1 equal to P2. We're going to set our momentums equal to each other. At phase 1, P1 equals M1 V1 equals P2, which is M2 V2. We have our mass 1, which is just the 3,500 kilograms. We have our V1, which is 8.8. Our M2 is going to be these two things added together, and our V2 is what we're going to solve for. So V2 is equal to M1 V1 over M2. Like we said, our mass 1 is 3,500 kilograms. Our V1 is 8.8 meters per second. And then our M2 is going to be 3,500 plus 20, so 3,520. Plugging all that in, you will get a new speed of 8.75 meters per second. And then if we think about this logically, it reduced a very, very small amount. It makes sense it would be reduced because it got heavier, and if it's heavier, it's going to be harder to move. And then it also reduced only a very small amount because 20 kilograms is not that much compared to a 3,500 kilogram truck. Now, we'll talk about this next section, but this is getting into our idea that we're going to expand a lot more later, which is the conservation of momentum. The fact that our momentum did not change meant that momentum was conserved in this problem. That's all I got for this video, though. Hopefully that makes sense. If you have any questions, please shoot me an email. Otherwise, this is Mr. Diamond signing off. Have a good rest of your day, everybody.